Welcome back, space enthusiasts. Today, we're diving into a groundbreaking discovery that has the entire scientific community buzzing. The James Webb Space Telescope, our window into the furthest reaches of the universe, has just observed something extraordinary, something that lies beyond the dark ages of the cosmos. But what it found left everyone astonished. So buckle up as we journey through time and space to uncover this incredible revelation. Before we get to the jaw-dropping discovery, let's understand what we mean by the dark ages of the universe. This term refers to a period after the Big Bang, when the universe was still in its infancy, around 400,000 to 1 billion years old. During this era, the universe was filled with a thick fog of hydrogen gas, which absorbed light, making it incredibly difficult for us to see through. It was like looking into a room filled with smoke. This period ended when the first stars and galaxies began to form and ionize the hydrogen, clearing up the cosmic fog. Until now, observing objects from beyond this time has been almost impossible. But with the James Webb Telescope, all of that has changed. The James Webb Space Telescope, or JWST, is the most advanced space observatory ever built, designed to look back in time to the earliest moments of our universe. Launched in December 2021, it orbits the Sun about 1.5 million kilometers away from Earth at a point known as Lagrange 2. Its infrared capabilities allow it to peer through cosmic dust and gas, seeing what no telescope before it could. Unlike the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, the JWST's infrared eyes are perfect for looking at distant objects. These objects are moving away from us so quickly that their light is redshifted beyond visible wavelengths. It's like having night vision goggles that can see through the veil of time and space. And now, for the big reveal, the JWST has spotted a celestial object that dates back to roughly 13.5 billion years ago, just a few 100 million years after the Big Bang. This makes it one of the oldest, if not the oldest, object ever observed. This object, named CEER S93316, is a galaxy, but not just any galaxy. It's an incredibly bright, compact, and surprisingly mature galaxy for its age. Scientists expected to find only young chaotic galaxies from this time, but CEER S93316 seems to have already developed a complex structure, challenging our understanding of how quickly galaxies formed and evolved. This discovery could potentially rewrite our cosmic history. This discovery has profound implications for our understanding of the universe. For starters, it suggests that galaxies might have formed much earlier and more quickly than previously thought. If a galaxy as well formed as CEER S93316 existed only a few 100 million years after the Big Bang, what other secrets might the universe be hiding from us? This could mean that the processes driving galaxy formation and evolution are far more efficient than we believed. It could also prompt new questions about the nature of dark matter and dark energy, the invisible forces that shape our universe. The JWST has essentially opened a new chapter in cosmology, providing us with a treasure trove of data that will take years to fully understand. The James Webb Telescope's journey is just beginning. With its unprecedented capabilities, scientists are excited to use it to explore even further back in time, closer to the moment of the Big Bang. Future observations will focus on finding even older galaxies, as well as studying the atmospheres of exoplanets to search for signs of life. The JWST will also look at the supermassive black holes that sit at the centers of galaxies, including our own Milky Way. Each discovery is not just a scientific milestone, but a step closer to answering some of the most profound questions we've ever asked. How did the universe begin? Are we alone in this vast cosmos? And what else is out there, waiting to be discovered? Now, let's dive into what scientists call the cosmic dawn. This period marks the transition from the Dark Ages to a universe filled with light, as the first stars began to ignite and form galaxies. Understanding this era is crucial because it's the universe's coming-of-age story. By studying these earliest sources of light, astronomers hope to uncover how the first galaxies influenced the evolution of the cosmos. With the JWST, we can finally observe this critical phase directly, rather than relying on simulations or indirect evidence. This could help us pinpoint when and how the universe made its dramatic transformation from a dark, lifeless expanse to the complex, vibrant cosmos we see today. One of the most intriguing goals of the JWST is to find population II stars, the very first generation of stars to form in the universe. These stars were massive, burning incredibly bright and hot, and they lived fast, dying in spectacular supernova explosions. Unlike the stars we see today, population II stars were composed almost entirely of hydrogen and helium, the only elements created in the Big Bang. Their explosive deaths seeded the universe with heavier elements like carbon and oxygen, which are essential for life as we know it. Spotting these ancient stars would provide a direct glimpse into the processes that made life possible. Following the cosmic dawn, the next significant milestone in the universe's history was the epoch of reionization. During this time, radiation from the first galaxies ionized the hydrogen atoms in the intergalactic medium, clearing the way for light to travel freely across space. This era is crucial for understanding the large-scale structure of the universe, as it marked the end of the Dark Ages. However, the details of how reionization unfolded remain elusive. The JWST's high-resolution observations can map this epoch in unprecedented detail, shedding light on the processes that reionized the cosmos and allowing us to see the universe as it took its first steps towards becoming transparent. When we talk about looking back in time, we're not just being poetic. Thanks to the universe's expansion, distant objects appear redshifted, meaning their light is stretched into longer, redder wavelengths. The further away an object is, the more its light is redshifted, allowing telescopes like the JWST to see these ancient sources of light. The JWST's ability to detect these faint, redshifted objects gives us a window into the past, enabling us to witness the birth of galaxies, the formation of the first stars, and the processes that shaped the universe. Each new discovery adds another piece to the puzzle of our cosmic history. What makes the discovery of galaxies like CEERS 93,316 so surprising is how mature they appear. According to previous theories, early galaxies were expected to be small, chaotic, and irregular. But the JWST has shown us that some galaxies were forming and organizing much faster than we thought. This means our models of galaxy formation and evolution might need a major overhaul. Perhaps the universe had mechanisms to accelerate galaxy growth and complexity much earlier than anticipated. Understanding these processes will be key to piecing together how galaxies like our Milky Way came to be and why some regions of the universe evolved differently than others. Another puzzle involves the presence of supermassive black holes at the centers of early galaxies. These cosmic giants, with masses millions to billions of times that of our Sun, were thought to take billions of years to form. However, the JWST has found evidence of supermassive black holes existing when the universe was less than 1 billion years old. How could such enormous objects form so quickly? This question challenges current theories of black hole formation and growth. Understanding these early black holes could unlock secrets about the birth of galaxies and the role black holes play in their evolution, influencing star formation and galaxy structure. Dark matter, the invisible substance that makes up most of the universe's mass, played a crucial role in the formation of the first galaxies. It acted as a gravitational scaffold, helping to pull gas together to form stars and galaxies. However, the details of how dark matter influenced early galaxy formation are still unclear. The JWST's observations of ancient galaxies will help us test theories about the nature of dark matter. By comparing the distribution and properties of early galaxies with predictions from simulations, we can gain new insights into this mysterious component of the cosmos. which remains one of the biggest unsolved puzzles in physics. The universe is not just a random scattering of galaxies. It's organized into a vast, interconnected structure known as the cosmic web. This web is made up of dark matter filaments, along which galaxies and clusters of galaxies are aligned. The spaces in between, called voids, are almost empty of matter. By studying the distribution of galaxies observed by the JWST, we can trace the cosmic web back to its earliest stages. This will help us understand how the large-scale structure of the universe formed and evolved over billions of years, revealing the intricate dance of gravity that shaped the cosmos. One of the most exciting tools in the JWST's arsenal is gravitational lensing. This phenomenon occurs when the gravity of a massive object, like a galaxy cluster, bends and magnifies the light from objects behind it, much like a giant cosmic magnifying glass. Gravitational lensing allows astronomers to see objects that would otherwise be too faint or too distant to observe. The JWST is using this technique to peer even further back in time, capturing detailed images of galaxies that formed just a few 100 million years after the Big Bang. These observations could reveal new insights into the very first stages of galaxy formation. Before the era of the Dark Ages, there was a period known as cosmic inflation, during which the universe expanded exponentially in a fraction of a second. This rapid expansion smoothed out the universe and set the stage for the formation of galaxies and large-scale structures. While the JWST can't directly observe inflation, its observations of the oldest galaxies and cosmic microwave background radiation can help test theories about this mysterious period. Understanding inflation is crucial because it's linked to fundamental questions about the origin of the universe, the nature of space-time, and the laws of physics themselves. Beyond exploring the early universe, the JWST is also equipped to study planets orbiting stars outside our solar system. Its powerful instruments can analyze the atmospheres of these distant worlds, searching for chemical signatures that might indicate the presence of life. By looking at the light from these planets as they pass in front of their host stars, the JWST can detect gases like water vapor, carbon dioxide, and even methane, which could hint at biological activity. This ability to peer into alien atmospheres represents a huge leap forward in our quest to find life beyond Earth. When searching for potentially habitable exoplanets, scientists focus on the habitable zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface. The JWST's ability to study exoplanet atmospheres means we can now better assess the habitability of worlds in these zones. By analyzing the chemical composition and weather patterns of exoplanets, scientists hope to identify those that are most likely to support life. This could one day lead to the discovery of a second Earth, profoundly changing our understanding of our place in the universe. One of the most exciting targets for the JWST is the TRAPPIST-1 system, which contains 7 Earth-sized planets, 3 of which are in the star's habitable zone. This system, located just 40 light-years away, is a perfect laboratory for studying the atmospheres of rocky exoplanets. The JWST will look for signs of water, ozone, and other molecules that could indicate the presence of life. Even if we don't find definitive evidence, these observations will teach us a lot about the variety of planetary environments out there and how common potentially habitable worlds might be. While the JWST is focused on the early universe, it's also designed to study galaxies far beyond our own. By observing distant galaxies in detail, we can learn more about how they evolve over time. This includes understanding the role of star formation, the impact of supernova, and the growth of supermassive black holes. These observations will help us see how different environments and conditions shape galaxies, leading to a better understanding of the diversity of galactic forms and behaviors across the cosmos. The James Webb Space Telescope marks the beginning of a new era in astronomy. Its ability to peer into the past and see the first galaxies, study the atmospheres of exoplanets, and explore the mysteries of the universe is unparalleled. Every image and data point collected by the JWST has the potential to rewrite textbooks, challenge our understanding, and inspire the next generation of scientists and explorers. As we continue to uncover the secrets of the cosmos, one thing is clear: the JWST is not just a telescope, it's a time machine, a window into the unknown, and a testament to human curiosity and ingenuity. The discoveries it will make in the years to come will shape our understanding of the universe and our place within it. The JWST's ability to look back in time is not just limited to observing the early universe. By examining galaxies at different stages of development, we can build a timeline of galactic evolution. This involves studying how galaxies change shape, grow in size, and undergo periods of intense star formation. For example, some galaxies, like our Milky Way, have a spiral structure, while others are elliptical or irregular. The JWST will help us understand how these different structures form and evolve. By piecing together the life stories of these galaxies, we can gain a better understanding of how the universe as a whole has matured over billions of years. A key aspect of understanding galaxy evolution is studying how stars are born. Stars form in dense clouds of gas and dust known as nebulae. As gravity pulls material together, these clouds collapse, heating up until nuclear fusion ignites, creating a new star. The JWST, with its infrared capabilities, can peer through the dusty envelopes of these stellar nurseries, revealing the processes that govern star formation. By observing stars at different stages of their birth, the JWST will provide critical insights into how stars of various sizes and types come into existence and how their formation influences the development of their home galaxies. Stars don't live forever. Massive stars, in particular, end their lives in dramatic supernova explosions, releasing huge amounts of energy and scattering the elements they've created into space. These supernovae play a crucial role in enriching the interstellar medium with heavy elements like iron and gold, which are essential for planet formation and ultimately life. The JWST will be able to observe the remnants of these explosive events in distant galaxies, helping scientists understand the conditions that lead to supernova and their impact on the surrounding environment. By studying these cosmic explosions, we gain insight into the life cycle of stars and the evolution of the elements that make up everything around us. While stars are being born, planets are also forming from the leftover material in the surrounding disk of gas and dust. These protoplanetary disks are the birthplaces of planets, moons, and other celestial bodies. The JWST can study these disks in unprecedented detail, providing clues about how planetary systems, including our own, come together. By observing young stars surrounded by these disks, we can see the early stages of planet formation, from small dust grains sticking together to the creation of full-sized planets. This knowledge helps us understand not just how our solar system formed, but also the diversity of planetary systems throughout the galaxy. Not all objects formed in these disks become full-fledged stars. Some, known as brown dwarfs, don't have enough mass to sustain the nuclear fusion that powers stars. They are often called failed stars because they sit in the gray area between the largest planets and the smallest stars. The JWST can study these elusive objects, which emit. But water isn't limited to planets and disks. The JWST will also search for water in comets, asteroids, and even interstellar clouds. By understanding how water is distributed throughout the universe, we can piece together the story of how this vital ingredient for life and on comets, suggesting that the basic ingredients for life are widespread in the universe. The JWST will explore these molecules in a variety of environments, from the coldest, darkest regions of space to the warm atmospheres of exoplanets. Understanding how these molecules form and survive in space can provide important clues about the potential for life to develop elsewhere in the cosmos. The JWST isn't just looking at distant stars and galaxies. It will also help us understand our own cosmic neighborhood. By studying the outer regions of our solar system, including the Kuiper Belt and Oort cloud, the JWST will provide insights into the formation of our own planetary system. Observations of distant, icy objects like Pluto and other dwarf planets will reveal information about the building blocks of the solar system and the processes that shaped its evolution. These observations will complement data from missions like New Horizons, giving us a fuller picture of the history of the solar system. The JWST's ability to study the atmospheres of planets isn't limited to distant exoplanets. It can also observe the gas giants in our own solar system, like Jupiter, Saturn, Uranus, and a trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blesovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.